Hello, everyone. I'm Jeffrey Gochuku. I'm one of the developers and developer relations of BIG Project and one of the presenters of this wonderful IMC. Today, we're going to learn about the basics of logistic regression and more. So now you may be asking, what is logistic regression? Logistic regression is a classification technique in machine learning where we classify data into two different groups. Use. Now, the real question is, what are the applications of this in the real world? Well, you've seen this many times as a student at university or even K-12. An example would be that teachers have a certain threshold in terms of like the minimum percentage to pass a class. And if you meet this threshold, you're clearly going to pass the class and you should be able to do well in your other classes in the future that require this current class. However, if the other case happens, then you're going to fail the class, but then you have to retake it so you can become better at that class and to really understand the concept of future classes in the future. So don't forget to study hard, kids. So the model we're going to, not the my God, the data that we're going to use today for logistic regression will be UCS's heart disease data. Now, why should we pick this data set for an example of this presentation? It's because this can help heart disease surgeons figure out whether they classify their patients correctly if they have heart disease or if they don't have heart disease. You could potentially save many lives without worrying. You could potentially save many lives by doing this right, or you could potentially destroy many lives if you made a mistake. So, so in terms of explaining morality behind these concepts, we should understand the concepts of what true, false, positives, and negatives are. So a true positive is when the sample data is actually in the positive class. In our case, we assume that the positive class is if the patient is actually diagnosed, meaning that if it's in the true positive class, this means that the patient actually does have heart disease. The true negative is when the sample data is actually in the negative class. In our case, negative really means misdiagnosed, meaning that patients actually don't have heart disease, so they're all good to go and they can go back to their families. False positive is when the sample data is incorrectly placed in the positive class. This means that in our case, we assume that the patients do have heart disease, but they actually don't. The real issue with that is if we spend so many times and resources on operating on a patient that doesn't have the disease in the first place, then the doctors are wasting their time and they could have saved other lives that actually have this problem. Now, the false negative is when we put the sample data in the negative class. This means that in our case, we assume that the patient has a misdiagnosed with heart disease and we let them go. But however, they could have a heart attack at any minute and the doctor may not even realize it. They could have potentially costed a life. And that's what we're here today to try to solve this problem. So now we should get into the interactive component of this activity. Now, before we start working on this, you should have all the prerequisite materials to prepare for this activity. You also need R installed because this is the programming language you're using. RStudio is pretty optional, but it's really convenient for looking at like the statistics regarding your data and looking at the visualizations while you're running your code at the same time. I personally use it all the time throughout my statistics coursework and projects. It's a really great tool to use instead of Baseline. Carrot. Carrot is the primarily machine learning package that was built in order to do train test split for machine learning models. Diplo is a really great R package to make sure that it's easier to manipulate data, whether there is missing values or even having an easier time cleaning it. CA Tools is a really good R package to optimize logistic regression models, which is why we're using it in this presentation. So the first step is to load the heart disease dataset. We would first make sure to import the necessary libraries at the top first so that R can recognize them. And then the second step would be to file path the file that you saved it in on your computer in the read.csv function and store it as a variable. And then we shall look at the first 6 rows of the given dataset so we can look at all the other features to determine which ones would match the best in terms of making a good logistic regression model. So these are the given 6 rows of the dataset, and we can tell that A lot of the 14 columns seem to be pretty relevant in terms of figuring out whether the patients are diagnosed correctly for heart disease. Now, if you look at the target column in particular, the target column represents the true classification, not the true, the dependent variable in our data set in terms of classifying the patients in either misdiagnosed or diagnosed. In our case, the ones represent the patients that have been misdiagnosed with heart disease, and the zeros represent the binary case where the patients have been diagnosed with heart disease. The next step is to look at the summary statistics, is to look at the spread of the distribution of each patient per column. As you can see here, these are the necessarily quartile ranges that represents each column, whether it be from the lowest to the highest. So even looking at the average to make sure where many of the patients are in these values. The next step is to look at the names of the chests to distinguish which columns seem to be very relevant in the actual model building. Now these are all the 14 same columns that you have seen before again. What I personally recommend is to choose like the sex column because this can classify the patients in terms of like their sexual identity, not sexual identity, but the two primary sexes, male and female. And then the second one would be the CP column, which explains like the chest pain levels that the patient could have. It can easily be misconstrued as something as simple as angina, meaning that they probably don't have that high of a cholesterol level compared to someone who has a full-blown heart disease. The last column is also a pretty relevant column because the maximum heart rate can be misconstrued as the patient's just over-exercising rather than the heart rate raising really fast because there's something wrong with them. The other column I recommend is the old P column, or the SC depression. The second one would be the, oh, I forgot, oh yeah. The SC depression is actually the average heart rate that the patient has, so you have to make sure that that's in control. The CA column would represent the number of blood vessels that are colored by a fluorescence, so it can measure the level of cholesteric plaque that's in the patient's arteries to determine if they truly have heart disease, or at minimum, at a very high risk of the disease itself. So the next step would be to do a train test split of the model. Now, why are we doing a train test split? It's because we want to determine, we got to give a certain percentage of the data that the model can learn from first before it works on newer data it's never seen before. But this also explains why the train model is at a high percentage at 7%, because again, like I said before, you have to make sure that the model is very familiar with the data it's working with before it works on new data it has never seen before. So it can make less errors later on in this analysis. So these are the fitted model statistics that are given here. Looking at it, looking at the p-values column, we can tell that all of them have all the columns that we have selected have a p-value that's less than the significance level of 0.05. This means that these columns are actually very significant in determining how it can affect the accuracy level of the model to determine whether the patients actually have heart disease or they don't have heart disease. The next step is to create the prediction variable using the testing data to determine how well our model will do with new data it's never seen before. So these are the fitted model statistics using the predictive variable that we just created. As you can see, apparently the predictive model knows that the majority of patients have been misdiagnosed. We're not fully sure if this is a good thing. We could assume that either the doctor legitimately made a mistake, but who knows? It turns out they could be incorrectly misdiagnosed, but could have the disease. We will find out more about that in the next slide. The final step is to create the confusion matrix, which will contain the accuracy level, the confidence interval for the true accuracy level, and the true, false, positive, and negative rates in our calculation. As you can see here, we have an accuracy level of 80.22%. This means that a model is very accurate since it has a higher accuracy greater than 50%, which is the average, meaning it's in between of being pretty, not being really good, but at the same time, it's not really terrible. And then the confidence interval is between 70.55% and the 80s and 87.85%, which means that overall our model is still pretty accurate because again, that range is greater than 50%, which means that we can truly determine whether the patients were diagnosed correctly or incorrectly. Now, to look at the true positive value rate, we have an 80.49% accuracy level, and the false positive rate is 19.51%, which you take that from 1 minus the true positive value. This means that the majority of patients were correctly determined to actually diagnose with heart disease. So that means the doctors made a lot less mistakes on average. The same thing can be said with the true negative value, where the average value, the average accuracy level is around 80%, and the false negative value is 20%. This means that on average, the majority of patients are going to be correctly misdiagnosed with the disease, so the doctors actually know where to allocate their time and resources on for the right patients. So for the most part, our model did a really good job in terms of determining whether the patients are actually sick or if they're really healthy. But however, the small error can still be an issue. Like if we explain how the 19.51% of patients that have been falsely diagnosed with heart disease, it's like I said before, the doctors could be wasting their time and resources on patients that are actually perfectly healthy, but it could be helping other patients that are actually have the disease itself, or potentially other diseases later on, and they could be at a lower mortality rate because of the time they wasted on a patient that's perfectly fine. Another consequence with the false negative here is that we assume that the patient is actually misdiagnosed, meaning that we let them go scot-free. But however, what if they have another heart attack without the doctor realizing it, and they still can get help on time? The doctor could have costed the life of that patient and will have to suffer the consequences. And overall, logistic regression is a very important model to implement so that we can correctly classify the values of our data in two binary groups so that you can make less mistakes in the future when you do your further analysis. Well, I'm glad that you guys had the time to listen to me give this very important lesson, and I hope you enjoy the rest of the IMC.